Randy, come in. I'm going to try not to impede your understanding of topological defects in crystals and liquid crystals. Please ask me any questions. I hope this is supposed to be informal. Let me start by just showing you some pretty pictures of liquid crystals. So liquid crystals, as you may know, or some of you may know, are these, it's a funny word, liquid crystals. If you were here 3 weeks ago, you could have heard Tim Slukin wax rhapsodic about, why it's called that at all. But there are things that are not quite liquids and not quite crystals. There really are liquids. They flow, but they actually have different phases. So who learned there were 3 states of matter? Want to raise your hand? Okay. 3 states of matter. Okay, how many states of matter did you learn about? Because you didn't raise your hand. States of matter, like when you're in high school or elementary school, your teacher says, how many states of matter? What? So, come on, louder. 3. And then sometimes they say 4 at museums. They say plasma, right? Okay. But it turns out that's not true. There's these tons of states of matter. All these liquid crystals are other states of matter. They're actually stable regions of the phase diagram. There are phase transitions between them. All right? And the isotropic is the regular fluid you think of, although here I'm making it a fluid of rods, right? And so the rods can order themselves. So I can have a situation where the centers of masses are, of course, not organized in any way, but all the molecules are pointed in the same direction. So that's certainly more order than a regular fluid, but it requires the molecules themselves to be long in some funny way. And of course, the really exciting thing is that they are optically interesting. That is to say, they're birefringent. They have different dielectric properties depending on their orientation. Or rather, they always have the same dielectric properties, but the polarization of light interacts with their long and short axes. And as a result, you can make wonderful displays and things out of that. And anyone know the revenue, the annual revenue, worldwide revenue for liquid crystals? You want to guess? You can do it in dollars or pounds. It won't matter. I'll just ask for an order of magnitude. How many zeros? 7. 1 million?
No.
10 million? Not even close. 100 million? Add 3 zeros? What is that? 10 billion? Nope. It's $100 billion a year. It's amazing to think about it, right? That $100 billion a year is spent on liquid crystals. But of course, think about how many liquid crystals are in this room. I don't mean in moles. I mean just think about displays. Right? In moles, it's even bigger, right? Okay. So they make all sorts of structures. They make as you cool them further, they make this really cool phase. My favorite phase, the smectic phase. This is a phase which is crystalline in one dimension, so it's actually nicely layered. But in each of these layers of molecules, it's actually fluid. So it's 2D fluid, 1D crystal. What does that mean to you? It means a fluid. What does a fluid mean? Or what does a fluid mean to me? A fluid means that if you take the top of the fluid and you push it really slowly, you make a shear, it just relaxes. It doesn't push on the bottom, right? There's some transient, but if you do it really slowly, nothing happens. And after time, there's no force on the bottom. Whereas if you have an elastic solid, if you hold the bottom and you push the top, there's always a force trying to restore it back. Something that's part liquid and part solid means that it does this in some directions, but not in others. If I take the top and I push it across to the bottom, nothing happens because it's fluid. There's no transmission of information or of registry from the top to the bottom. But if I try to shear it this way, I'll know. Okay, so that's what it means to me. We'll talk about smectics. They enjoy all sorts of defects. I don't know why the next slide is blank. Oh, I do know. It's supposed to say, let me show you some real pictures now, okay? Ready? Look at that. Really cool. This is called a Schlieren texture. Schlieren means, anybody German in here? He left. Holger left. He never comes to my talks. Yeah, what does Schlieren mean to you?
What do you see?
Yeah, but what does it mean? It just means a mess, right? Okay, a schmear. It's just a messy texture, right? It's not a person. There was no physicist named Schlieren, as far as we know. So I'll explain this later. Here's a picture. This one has a name. This is called the greasy smear texture. I know it's weird. This is DNA. It turns out DNA makes liquid crystals. And the fact that you see a bunch of colors suggests what? Come on, look at the pictures. The whole trick is to look at the pictures and figure out what's going on. That's what theoretical physics is about, right? So here's the picture. What's going on? Take a guess. You could be wrong. It's okay. Anybody?
Different orientation.
Not you. You're the one organizer.
He said anybody.
I know. But, okay, fine. Go ahead, Daryl.
Means the different orientations of the DNA.
So somehow the DNA, though, must be making some sort of Bragg planes. There must be Bragg planes, and they must be pointing in random directions, right? And I'm getting different colors. Is it diffracting? Diffracting off of those Bragg planes. Okay. Here I have another thing. This is called a cholesteric. I probably won't talk about that in great detail, but you see these nice stripes here. These stripes are telling you something else is going on periodic. This, oh man, right? This means something's periodic and we're seeing diffraction. Here, we're just seeing stripes. I'd like to point out to you that this is a picture taken with a regular microscope. Okay, not an electron microscope, not a high energy collider, you know, in Switzerland or anything like that. Regular microscope, this is like microns across. So whatever these stripes are, they're big. The molecules are small. The molecules are nanometers, but these stripes are like microns, in the order of microns or hundreds of nanometers. Here's another picture with stripes. We'll get into this, what you're seeing. Here, this is liquid crystal physicists get to study this. This is the most beautiful and wondrous thing. This looks like a crystal, right? Who thinks it's a crystal? Raise your hand. Just from looking at a picture. Yeah, well, it's not. It flows. Okay? I know, it's a trick. This is actually a thing called, this is a material aptly named the blue phase, okay, because it's blue, but you can use Photoshop and change its color. And there are blue phases that are red and green and stuff. But what this is a crystal, but it's a crystal of orientation. So it's like saying at every point in space, there's some orientation. Those rods know which way to point everywhere in space. And it's a 3D pattern of orientation. Not a 3D density wave, a 3D pattern of orientation, which facets. There's a Wolf construction, blah, 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 right? It facets just like a regular crystal, but it's faceting because of orientation, not because of density. Or if Tom Lubensky were in the room, he would say, yes, but of course, there is a density modulation. It's true. It's weakly coupled. There's a weak coupling between the orientation and the density, but even in the absence of density, you would get this orientation. Is Holger back in the room? Still. Oh, there he is. Do you know anybody who's written a thesis on this? Many theses on this. And am I correct in saying that it works even without a density wave?
Yes, you are allowed.
Okay, thank you. We were office mates a long time ago. And here is a picture of a smectic. And I don't know, does this look to you like monofilaments? Remember that was a long word for fish? Does it look like fish? To me, it always looks, like fish. Oh, man. I have to go back through it now, right? So here you have these things. It turns out, if you look at it really carefully, there are actually pieces of conic sections there, right? And I would refer you to the literature to understand where that's from. But the conic sections, you can see very, very sharp ellipses. Basically, this is a bunch of ellipses that are spread out over the surface. This is a telltale sign that you have a smectic liquid crystal. And I wish I had, time to explain all these things. There will be references later, and you should certainly ask me for anything. And I'm lecturing again on Friday, so if there's anything that catches your fancy, tell me at the end of this, and I could change my lecture. Okay, until Friday. So here, I just want to show you this movie, parts of this movie. So I know, because this is about, the workshop's title something about dynamics. Is that right? So here's dynamics. This is a liquid crystal doing its thing. Do you see the conic sections? Do you see the ellipses there? These ellipses, what this is a regular regular liquid crystal. There's temperature gradient. Where you see black, it's isotropic. Where it's not black, you're starting to see different phases. This is the smectic phase. Just from looking at the picture, you see a bunch of things. Well, here, watch this. See? First of all, you can tell the order of the transition. Do you have a sharp line between the two things? the two phases, or a smooth line, right? A squished out region. You can decide whether it's first or second order. Here, watch this. Is this first or second order? Come on. Why second? Do you have droplets when you have second order transitions? No idea. First order transition, ice floats in water. First order transition, there's a latent heat. So you have interfaces, you have coexistence of different phases. Second order transitions, bam, the whole thing goes. Right? The magnet decides, I'm a magnet, bam, I'm going to point in one direction. Okay? So you can tell a lot just from the pictures. And I'm going to tell you today, and on Friday, what else you can tell from the pictures, because there's lots to tell from these pictures. And of course, it's much easier if you could just look at these pictures taken with a regular microscope and try to understand what we have. I want to whet your appetite. These are topological defects. These lines here, they're vortices in a nematic, and I'll make it clear what I mean by vortex and nematic before this is over. It reminds me, there's this book by Meyer Jerison. It's called Rings of Continuous Functions. Anyone know this book? I'm sure it's in the library, right? You know this book? Yeah. And it says, at the beginning, it says, this book is intended for people who know what every word in the title means. None will be defined in the text, right? So, but I'll define things. Okay, so here is two spheres, two colloidal spheres, which have interesting boundary conditions. Watch what happens. Okay, here are some defect lines that over time coarsen, and they end up making this pattern, this sort of two spheres connected by this complicated rubber band. Watch the experiment on the right now. Okay, the experiment on the right, all they do is they have these two colloids. The boundary conditions are the pneumatics, those rods. The rods want to be perpendicular to the surface of the sphere. They zap the whole thing with a laser, going from the pneumatic state to the isotropic state. The isotropic state then quenches back in the pneumatic state, and you get a mess, a jumble of defects, and the defects coarsen over time, and it gives you exactly the same thing. Pretty cool, okay? So there's actually, it's quite a sophisticated field, and that is lots is known and lots works. However, you can see this is still really simple compared to that movie I showed you, right? So what you can extract from the system without having to go into the details of the molecules is better, and let's start here. So this is your Schlieren texture, all right? It's a two-dimensional pneumatic. So what do I mean by that? There are molecules, those rods, they lie in the plane. What do you see when you see this? Well, one thing you see is you see these black lines. But then you see that the black lines come together at these junctions, 4 at a time. Sometimes 2 at a time. But never 3 at a time. Never 5 at a time. Black lines never just end. So that's a piece of interesting information. What are we looking at here? Well, here's the experimental setup. You have a light. You have a polarizer. So now you have polarized light. You have an analyzer, which is actually a polarizer also, right? What happens if you take two polarizers that are crossed like this and you send light through them? Anybody? What? Black. Excellent, right? But the molecules in between, which lie in the same plane as the polarizer and the analyzer, they're birefringent. So the group velocity or the phase velocity, I guess it's the same, right? The phase velocity is different for light that's polarized along the rods and perpendicular to the rods. And as a result, if you send polarized light across these rods, the two different parts don't meet and cancel each other at the other side, and some light gets through. So because they're birefringent, you actually get light going through the sample. So what? So look at the picture here. So I have light. That's why light goes through. I'm looking directly at this system. Right? If you were clever, you'd figure out a way of taking the molecules maybe and tilting them so that instead of lying in the plane, they were pointing from front to back. Then they would be not birefringent anymore. They would be round. Yes? And then you get black all the time. Hey, you could, by switching them, you can make it go from colored to black, right? From light going through to black. You can make a display. That's how displays work. So now you know how displays work. Okay, but that's the $100 billion a year industry. But you still get black lines here. Why do you get black lines? I know the answer.
Grain boundaries.
No.
Defects.
No. You're just looking through a list of keywords. Why do you still see black sometimes? In this setup, do you always see, does light always get through? If the molecules happen to be parallel to either polarizer, then you also don't get anything because there's only one wave that goes through. And the two waves don't mix. There's only an extraordinary wave, or there's only an ordinary wave, or whatever you want to call it. So the black lines are actually telling you wherever the molecules are parallel to the polarizer and the analyzer. Pretty cool, okay? That's called the pre-image in topology, okay? I want the pre-image of all the directions, where all the places where the molecule is pointing along a particular direction. The black line is the pre-image of those two directions. So let me think about, why do I get those junctions where there were four black lines going to a point? Well, look, here is a defect. Here's a place where in the center I don't know which way the molecules are supposed to point, right? They point in these directions out here. Let me now cross out all the directions that look like point along the polarizer and all the directions that point along the analyzer. There's one. 4 brushes coming to a point. Here's another texture, totally different. You might have called this, I don't know what you'd call this, some kind of negative defect. Here's a positive defect where the things wind around. Nonetheless, 4 brushes. Here's another one. I don't know what you call this, a fountain, okay? Badly combed hair, okay? Here's one like extensional flow or something. 4. Why 4? The molecules, when you go around a closed circuit, you can go clockwise or counterclockwise, whichever you like. Right? When you go around a closed circuit, the molecules have to come back to which way they were pointing, unless you're at the defect where you don't know anything. But everywhere else, the molecules, the direction of the molecule is single valued. When you come back around, the molecule has to rotate by 2 pi. That means it has to go through the polarizer direction twice and the analyzer direction twice. 4 brushes. Okay? So why do I see 2 brushes? Remember I showed you 2 brushes. Look at this. This is a picture taken with a microscope, the kind of microscope that was invented, I don't know, they're not 1,000. How old is a microscope? 400, 300 years? I mean, same as Galileo. Who thought about turning the telescope around? I don't know, that guy, Brown. Brown definitely did it, right? That was like one of the first things he saw, Brownian motion, right? But there were people, I don't know, it's at least 100 years old. Certainly, sorry?
Moving book or something like that.
Okay, a Dutch guy. Okay. Microscopes are old. It's an old technology, all right? Here you are looking at a microscope with polarizers. Polarizers, I know, were around the 1820s. They were invented by Arago, all right, to great use. Here you go. Here are the polarizers. Why do I see 2 brushes? Remember, you get a black line when it goes through the polarizer direction and a black line when it goes through the analyzer direction. It must be that it's not going around 2 pi. It must be only going around pi. It's going through the polarizer once and the analyzer once. That means that the molecule, this and this, are actually the same. Like I drew them. They're ellipsoids. When they rotate by pi around their axis, they're actually identical. So single valued is more subtle. It doesn't have to go around by 2 pi. Going around by pi still yields the thing as a single valued field. So look at that. Just from looking at this, I now know, looking at the topology, seeing that I have 2 brushes, is enough information to tell me about the symmetry of the molecules or the molecular phase down at the nanometer level. Okay? So that's my hope. My dream is that by making observations just like that, counting, we can understand all liquid crystals and all those movies and all those dynamics. All right? That's my dream now, to have you guys, go forth and do this. Okay? Let's see what else I want to show you. So now, looking at this, that's the Schlieren texture. That's the 2D nematic. Again, we haven't talked about this, but those are these parallel planes. I'm just reminding you how pretty these things are. And I always say, we get to study things like this. All right, this is just an amazing phase of matter. Let me just tell you something. This is more foreshadowing than anything else. That liquid crystals, in addition, they have a free energy. Once you have this director, you can start talking about the elasticity theory for the director field. And there are these three textures. There's splay, where the molecules do this, and there's twist, where they do this, and there's bend, where they do this. And you can write that in terms of, regular derivative kind of things of, various, what is that called? Vector calculus derivatives, splay, twist, and bend. You can put them together into a free energy, where you have these elastic constants. This is the energy cost for having a splay mode, a twist mode, and a bend mode, like so. You can stare at this a little longer and note that this is a pseudoscalar, so you can add a constant. There can be a pseudoscalar term. That means when Q naught is not 0, it means that the system is not invariant under reflection or spatial inversion, right? Notice that n dot curl n changes sign under spatial inversion. So Q naught gives you a preference for which handedness things are. We'll get to that. Let me make a theory, by the way. Oh, man. Let's go backwards. Didn't used to be like this. It used to be you had transparencies and you couldn't find anything. Okay, there you go. So here are the elastic constants, or here are the modes. What are the elastic constants? I'm a theorist. We're duty-bound to try to predict or understand what those elastic constants are. Well, here's the cool thing. My advisor taught me this a long time ago. What energy scale does a liquid crystal exist at? What are the energy scales involved with all the liquid crystal molecules? Forget liquid crystals. What are the energy scales associated with the molecules coming together to make this beautiful wood laminate that the Newton Institute has provided? Or the material in your shirt? Anybody? What's the energy scale? What's the energy scale of all the things that we touch and feel and push on? All materials. The answer's there, so you could just say it. And I say, that's brilliant. Okay, try that. Try that. You try. KBT, it's brilliant. Okay? Right? What insight? KB, of course, is Boltzmann's constant. T is the temperature. Of course, I don't mean any temperature. I mean room temperature. Why should it be that everything has the energy of room temperature?
Brownian motion?
Brownian motion. Not everything has, this table is not, the molecules maybe have Brownian motion. That's actually the key idea, yes. Let's expand on it. Look, whatever the energy scale is that determines the properties of materials that we're aware of, all the materials we know of within an order of magnitude, they all melt, freeze, boil at about room temperature, right? A room order of magnitude is 30 to 3,000 Kelvin. All right, if I want 2 orders of magnitude, I'm going 3 to 30,000. That is almost everything. Okay? You have to work hard to get below 3 Kelvin. Right? That's superfluid helium, right? It's 2.7 Kelvin. So you have to work hard to get beyond that. Right? So most of the things that we know and touch and play with, they all kind of melt around 300 Kelvin. Agreed? So whatever the energy scale is, because melting, all those things are the balance of entropy with energy, it must be that the energy scale must be about room temperature. I'm not saying that everything's thermal. I'm just saying if it weren't that energy, we wouldn't be able to see transitions, in our lifetime. Okay, so that's the energy scale. What's the length scale? Well, the only length scale in a pneumatic is a perfect fluid where the molecules are all pointing the same way. The only length scale is the size of the molecule. They have infinite range order. So there's no droplet size. The whole thing is ordered. So the only length scale is the size of the molecule, 10 angstroms. Okay, the elastic constants have units of energy per unit length. You can put room temperature, a 40th of an electron volt divided by 10 angstroms. It's bad units, I know. It's half a microdyne. So that's just an estimate. That's a back of the envelope estimate of what the elastic constants ought to be. Let's check. Look at it. The very first one in the very first corner is 5 times 10 to the minus 7 dynes. Exactly 1/2 microdyne. Right? And of course, they're all on the order of a microdyne. and here's some other elastic constants, different liquid crystal molecules. They all roughly have that. So I kind of understand the elastic constants. What I don't understand is this funky value Q naught. And I already told you why I don't understand that. If I go back to the picture, I can find it. Oh, man. Who's ever been at a conference where somebody has a clicker that has the same wavelength as that clicker? Right? So I showed you, okay, here we go. I showed you this, right? So the wavelength is like the wavelength. The liquid crystal is making patterns. That Q naught gives you a length scale. It's making patterns that are hundreds of nanometers, right? If I go to this one, this is diffracting light. So if it's diffracting light, what's the wavelength? What's the length scale of the grating? Come on. If somebody's good at diffracting visible light, green light, what's its wavelength?
500 nanometers.
Excellent. So it must be something that's 500 nanometers in spacing. Isn't that weird? 500 nanometers is not 10 angstroms. Right? I told you there's only one length scale in the problem. When I look at the system, there's this one length scale. So trying to understand this other length scale, which is thousands times longer than the molecular length scale or any other length scale in the system, is very, very difficult. It's not easy to understand why. Blue phase is blue because of that. It's not easy to understand why those are. And again, I can't tell you more about that, but I can refer you to references. But the theory of those length scales is very difficult. The theory of the elastic constants is easy. So we understand some things, but not everything. Can I take the microphone off? No. Oh, she jumped out. Okay. All right. We don't need those lights on. That'll make us all hot. We just need the lights on the chalkboard. Okay. All right. So I've never used a chalkboard before, so you'll have to bear with me. Who's ever heard a lecture on a chalkboard? Raise your hand. That's it? There's 3 people? You've never heard a lecture given by a chalkboard? Ever?
I've heard of it, never seen one.
What about in college? In college?
Whiteboard.
Whiteboard.
Can I ask a quick question before you? So I thought that at a defect, that the plus minus a half, the plus minus was to do with which way the director rotates as you go around.
Yes.
Did we see that in the pictures? I thought.
You can't. Those pictures are stills. They're still lifes. So if you look at them, whether it goes around plus 2 pi or minus 2 pi, it'll always have 4 brushes.
Right. No, I was meaning whether it rotates clockwise or anti-clockwise.
Sure.
Around anti.
So the brushes don't give you the sign. They just give you the magnitude. But watch this. You ready? So here are the cross polarizers, and you have brushes. If I do this, the brushes will either rotate the same way that I go or the opposite way.
Right.
If they rotate the same way, I'll call them plus, and if they rotate the opposite way, I'll call them minus. And then you can figure out, yes, if they rotate plus, they're rotating counterclockwise, otherwise clockwise. Yeah, so you need to take 2 pictures to get the sign. Actually, really clever experimentalists, what they do is they don't use cross polarizers, they use skewed polarizers. They can get the information that way. Or they can guess the information. Okay. So, okay. So let's talk about the defects in the pneumatic. So let's go back to the 2-dimensional pneumatic. If my writing is too messy, I can't help it. But if it's too small, I can write bigger. Okay? So tell me if you can see this. We'll go back to the 2-dimensional pneumatic. And I imagine here I have this defect. And here's my sample, like so. And what I meant by a defect is a place where I don't know which way the molecule is pointing, or rather, the molecule doesn't know which way it's pointing. And there's lots of ways this can happen. If it were pneumatic, it could melt in the center and be isotropic. That's one way it could deal with that, because if it's isotropic, it doesn't have a direction. Or mathematically, I can say if there's a place where I don't know which way the pneumatic's pointing, there's a singularity, I will excise it. I will poke it out. And instead of thinking of the whole plane, R2, I'll subtract out the origin, or wherever the defect happens to sit. Okay? By the way, this backslash notation, does anyone know this? It's the minus. It took us, I would say, 3 months to read a paper once, because we didn't know what that meant. Right? It's very hard to Google a math symbol. Right? You can Google backslash, but it doesn't, it'll give you lots of stuff. All the tech commands start with backslash too. Right? And so, yeah, reading it dumbly, it's like, oh, this means actual brace, and this is the tech brace. We didn't have any idea what it meant, but we finally figured it out by context, because it was clear that's what they meant. So anyhow, here's your sample, and here's a piece of colored chalk. And so what I'm going to do is I'm going to do a measurement. Okay, I'm going to go around the sample. I'm going to go around this defect. I'm going to do a measurement on this curve gamma, and I'm going to assume. Let's see, what am I going to assume? I'm going to assume that I know the direction of the molecule. So everywhere in space here, I have some field n. Okay, this is the field n. N is a unit vector. Okay, I'm not going to worry. Let's not worry about n and minus n being equivalent. Right, let's not worry about that for now. That's an extra complication. It's a beautiful extra complication, but it's an extra complication. Let's just imagine it's a vector field living in the plane, unit vector. Everywhere in the plane, oh, n is also, let's see, n lives in R2. Okay? So it's a unit vector living in 2 dimensions. And what can I do? As I go around here, I can do a measurement. If I had a polarizer and an analyzer, what I would see, and I had light source, I would see 4 brushes if I had a 2 pi defect, or I'd see 8 brushes if it were a 4 pi defect, right, and so forth. They'd be multiples of 4. But what could I do? Suppose I know n. So what I'm going to do instead is I'm going to do an integral. And it's homage to Newton, right? Here we are at the Newton Institute, so we're going to do integrals. Okay, I'm going to do this line integral around this contour omega. I'm going to integrate ds. And then what I'm going to do is I'm going to calculate n cross dsn. Now, that's kind of a complicated thing to do, but what is this? Why is this interesting? Because over here, I have the unit circle that n lives in. This is the n space, right? So n lives, oh, if you close that, we're all going to die. You got to open that.
Should I open it?
Yeah, otherwise we're going to die.
Okay.
Because the wind won't do anything. Okay. All right. So here's n. So what's happening? Every point here, as I go around this yellow curve, gives me some point here, right? This is the unit. This is length 1. So every point here corresponds to a point here. It's a map from that circle to this circle. Yes? S1 to S1. Okay? So there's that circle, the yellow circle. Here, I'll make the yellow circle in yellow, so you remind and you know what I'm talking about. I'll make the 1 in yellow too, right? I have a map from the circle to the circle, and at each point, you're giving me a particular direction n. Here's n of s, like so. And dsn is how much? Right? This is dsn. So n cross dsn is telling me the signed length on this path. Right? Because it's telling n cross dsn is either pointing this way. If dsn pointed the other way, then it would be going the wrong way. Right? So it's giving me the signed length on, I don't know what to call this. I'll call this the Gauss map. It's not the Gauss map, but I'll call it the Gauss map. I'll put it in small. It's not really. We'll make up a new thing, because you guys are grinning at me. We'll call it the Tesla map, okay? Which is the map from the circle to the circle, okay? And so here's n, and n cross dsn is the signed length. So it's telling me how many times I go around. It's telling me whether I'm going around clockwise or counterclockwise. It's even allowing me to do that thing that Ptolemy invented. What's that called? Epicycles, right? I could imagine as I go around, right, as we go around, that n does this, right? N could be wobbling, right? N could be doing a lot of backtracking, but eventually, as I go around, n still rotates by 2 pi. But there can be backtracking and forward tracking. By having this be n cross dsn, this is giving me the sign length, and it ignores all those backtrackings. That's good, all right? Because I could have done something else, right? I could have, here's the alternative. I'll write it in a different bad color, red. Alternative. I could have integrated ds, the magnitude of dsn. All right? I could have done that. If I had, you notice that n is perpendicular to dsn because it's a unit vector, so the magnitude of this is the same as the magnitude of this. So I'm getting the same magnitude, but this doesn't have the sign. Right? It's the difference between, say, integrating, for instance, when you look at say, mechanics of rods, you can integrate the curvature of the rod, but you can also integrate the unsigned curvature of the rod. Right? And there are theorems that make that difference. So we're not going to do this. I want the sign length. By getting the sign length, I'm getting something that's nice and invariant. I'm getting something that's actually just giving me the information on how much n rotates around. Now, who's thinking this is awfully complicated? Here, raise your hand if you think it's awfully complicated. Nothing? Blank? You think it's awfully complicated? Because he says, oh, this is ridiculous. N's a unit vector. I can parameterize it by an angle. Right? Saying, what are you talking about? Right? I could just integrate ds theta. By doing that, it's clear that it's picking up only the net change in theta. This is telling me, say, theta at 2 pi minus theta of 0. Because n has to be single valued, theta has to change by a multiple, right? Theta of 2 pi minus theta of 0 must be an element of 2 pi z, so that n is single valued. Okay? See, I've never used a chalkboard before, right? And so that tells you that that's everything. And it's just giving me the jump in the angle. Okay? But I like this better. How many chalkboards are in here? Okay. So one thing that's nice, why the sign length? Or, oops. Why n cross dsn? Does the question mark go here? Yeah. Okay. First of all, I'll note that n cross dsn is the same thing as the determinant of the matrix made by these two vectors. Right? If the first row is n and the second row is dsn, it's just that determinant. You can say, so what? What it's doing is that determinant is how it is that I'm getting the sign length. When we go to signed area in higher dimensions, then it'll become obvious what to do. All right, so this is determinant. This is just a Jacobian going from the space here to the space there. All right, and because it's a Jacobian, it picks up whether I'm rotating the wrong way or the right way. All right, it's the unsigned, right? It's not the magnitude of the determinant. That's the Jacobian that you learn in elementary school. I'm sorry. It's the Jacobian that I learned when you were in elementary school. Okay? All right, so you don't take the magnitude of it, you actually take the signed determinant. Okay. I don't know, there's some word for that. I was looking through Daryl's books today for inspiration. Isn't it like called a pullback or a push forward or something like that? Which one? Depends which way I'm going.
Yeah, that's all fair.
I guess if I'm going from here to here, it's the pullback of the length to there. Okay. So that's it. So we get all the information we need when we study this, and we can even now define a charge, m, which is 1 on 2 pi, this integral around the contour, ds n cross dsn. And you're going to say to me, why would I do this? Well, m has to be an integer. Okay? I already established it has to be an integer. So now they've told you it has to be an integer. Why is that interesting from the point of view of dynamics? To me, one of the things that's great about topology is it actually gives you lots of information about dynamics. Why? Because if I smoothly deform the nematic texture and don't introduce any new defects or any new holes in the sample, I can either smoothly deform n or I can smoothly deform gamma, right? Because this integral has as its input not only the n field, but also gamma. It wants to know what path you take. It also wants to know what you're integrating. Both things are inputs. As long as that path never crosses anything that's discontinuous, as long as I don't tear the n field, this is an integer. And it has to be the same integer. As long as I continuously evolve the director field or continuously evolve the yellow curve without crossing through the defect, this is unchanged. Right? Why? Because the m is continuous under smooth deformations of n and gamma. And what integers, which integers are smooth under continuous deformation? Which integer valued functions are continuous?
Constant.
Are those the only? Yes, of course they are. How could it jump? It has to be discontinuous to jump from one integer to another. So isn't that cool? So under dynamics, whatever dynamics you write down, right, as long as your dynamics is nice and smooth, you know, evolution with differential equations and all that, that's even smoother, right? Then this integer m is constant. So these objects are long-lived until something catastrophic happens, where a singularity meets another singularity, or you tear up in the system. So again, under dynamics, this is why looking at those pictures is useful. Looking at those movies I showed you, if I can assign integers to different regions of space, those integers have to evolve continuously. And that means that they're constant and they're fixed. So if I can restrict myself and focus only on these charges, if you like, then I'm in good shape. Who's heard of Kossler-Salas transition? Come on, you said at lunch you heard of it. Raise your hand.
Yeah.
Okay, all right. See, all right, I planted you for this, right? So, you know, this is the whole thing behind Kossler-Salas phase transition, the Kossler-Salas theory of melting in two dimensions, Kossler-Salas, Halpern, Nelson, Young, and Berezhinsky. Okay? So the idea about these defects being the interesting objects. In fact, when you're lucky, you can take a system that has smooth things and these defects, and you can actually remove the smooth degrees of freedom, leaving behind only a theory of the defects. You can do that for the XY model, which is the Kossler-Salas transition, where you can have an effective theory just of the defects. You can do it for vortices in a superfluid. You can even do it for vortices in a superconductor, kind of, okay, where you integrate out the smooth part of the field. Who's ever done that? Nobody? Who's ever thought they could do that? Really? Nobody's ever done that? Well, you should all look tonight at Chaikin Lubensky and read how you can do the Kossler-Salas transition in terms of this. But all I want you to understand is that this is nice and conserved, locally conserved. There's a region where I can calculate some windy number, and it's a nice conserved number. Okay, any questions? Yes?
Did you mention before that we can have pi?
Yes, and I also said I'm going to ignore that. Let's not worry about n goes to minus n. But if I could have pi, then all that would change here is I'd be able to erase this. I know, that's like the most evil thing. Professors do it all the time. You guys can't erase like that. You're taking notes with pen and ink, and they just do this. Okay? Oh, now you have to rewrite all the notes? How can you now record that? But it's being videotaped, so you can watch it that way. Anyhow, I'll put the two back. Yeah, so I could say, if I know the molecules are the same, whether they're pointing up or down, then I can say it's up to mod pi. So I can put pi z, all right? instead then of having maps from S1 to S1, it'd be technically a map from S1 to RP1. But RP1 is the same as S1. We'll get into that, at least for my purposes. Okay. So let's generalize this. Suppose now, I need an eraser. Okay. Suppose now, I'm not going to do this piecewise. It's a joke. Okay. So now I have a 3D pneumatic. So when I have a 3D pneumatic, I can also have a point defect. So everything's going to be the same. I have a unit vector. It lives in R3, like so. Right? This whole thing lives in R3. So now I have a point defect. I have a place where, for instance, the director doesn't know which way to point. We'll come back to what happens. Well, so that's a possibility. For instance, imagine a situation where the pneumatic points out radially from the center. You could say it's like electric field lines from a point charge, but you shouldn't say that. Right? So it points out radially. So you can see at the center it doesn't know which way to point. Outside the center it knows which way to point. So I can imagine a point defect. And now I'm going to surround the point defect with a sphere. Like so. So here's the sphere. And I'm going to do exactly the same thing I did before. I'm going to now look at each point on the surface. And each point on the surface corresponds to a point over here. Oops. That is not on purpose. Okay. I had a chemistry teacher in high school who dropped things all the time like that, and it seemed like he was doing it on purpose. And then he explained to us once that when he was in graduate school, he found out that he said, I'd rather have a car than eat proper food. So he discovered, he was at college, he went to graduate school at the University of Illinois, which is a large agrarian state, okay, in the Midwest. And he discovered that you could eat monkey chow. And monkey chow was very inexpensive because they fed monkeys monkey chow at the veterinary school. So he actually decided for a few months to eat monkey chow in exchange for having a car. So I always think about him when I drop things. So maybe that's why. Anyhow, here is the pneumatic director. This is length 1, like so. Okay. So I have a map from the sample. Here's the sample map, and I can call this the director. Again, it's not quite the Gauss map. We'll continue to call it the Tesla map. Like so. All right. And for each point here on my sample, there's some point there. And now I want to calculate, instead of the signed length, I want to calculate the signed area that I sweep out. You ready? Well, how easy is that? All I do is I integrate. Yeah. Okay. I integrate over the whole surface. I have some coordinates on the surface, ds and dt, whatever you like them to be. And here's how I calculate the signed area. You ready? It's the determinant of the matrix made by this and this. All right? See, incomplete analogy that I did before. You give me some little piece of area here in the unit normal to the sphere. That corresponds here. The unit normal to this sphere is the unit vector n. And then I have the two directions ds and dsn and dtn. And dsn and dtn do not need not be perpendicular to each other. I don't need any special coordinates. N is perpendicular to both of them. Okay, so look, this is the complete this is the analogy to what I did before. This is giving me the signed area. So let me call it A tilde for for the signed area. What can you tell me about the signed area, anybody? Is there anything nice about the signed area? What nice things can you see about the signed area? Come on. I know you've taken math classes, so, you know, what's the first thing that a mathematician would ask you?
It's a two form.
I guess it's a two form. It never helps me, right? Is it a scalar valued two form?
No.
You sure? I think it's a scalar valued two form. As opposed to, they always talk about tensor valued two
No, it
form.
changes sign.
You can write the sign.
Yeah, but the components are scalars as opposed to tensors. Like the Riemann tensor is a tensor value two form. People always say that just because it sounds cool.
Does it exist and is it unique?
Yeah. It exists. I just wrote it down. But is it unique? And what I mean by unique, or what you should mean by unique, is what if I change the coordinates here? Right? But Darryl already said it. He said it in the more sophisticated way, so I'm embarrassed, which is, of course, it is a two form. And so if I make a transformation, suppose I have new coordinates, sigma of s and t and tau of s and t. Like, see, coordinate transform. Right? So sigma is this and tau is that. Then I can go ahead and calculate. I could calculate n. So that determinant, the determinant is equal to n dot ds d sigma n. Let's see, dsn cross d tau dt n, like so. But dsn is d sigma n. Let's see, d sigma ds plus d tau n d tau ds and dtn is d sigma n d sigma dt plus d tau n d tau dt. How exciting is that? And when I take the cross product, of course, you can see what will happen. I'm going to take the cross product here on this auxiliary board because it's not that interesting, right? When I look at dsn cross dt, and what do I get? Well, I get the cross product of this mess. Of course, dtn cross dtn is 0, and d sigma n cross d sigma n is 0. And I'm sorry for using crosses and dots and all that, but we're in 3 dimensions, so I don't need to do anything fancier. I get d sigma n cross d tau n times d sigma ds d tau dt minus d tau ds d sigma dt, which is the determinant of d sigma ds.
Randy, we can't read that.
Is it too small?
Color.
Oh, see, I told you it was unimportant. Okay. All right, what color would you like? Oh, no, white suggests it's important. Green, can you read this? How about this? Can you read this? Can you see that? Okay. By the way, you guys know that I mean d by ds, right? When I was in graduate school, I was a teaching fellow for this course called, I don't know, Architecture of the Structure of Matter, okay? It was a course for students who didn't want to, they weren't science majors. It was like part of their core requirement. Really, it was a course for people who didn't want, nobody in the room wanted to be there, okay? Right? I certainly didn't want to be there. The students didn't want to be there. And there was this student whose name I remember, but I won't say because it's being broadcast, and he may be a very rich possible donor, which is right before the final exam, the whole term, the instructor was using this symbol. Like, he probably didn't even use exponentials like that. That would have been too hard. Like that. Okay? You with me? This student came to me the day before the final exam and said, "What's this fish symbol?" Anyhow, so I just want to make sure if I use some notation that you're unfamiliar with, you should speak up. Okay, and then, so when I do this all, I get d sigma n cross d tau n times this determinant, which is d sigma ds, d sigma dt, did I do it wrong? You're just making noise, okay. D tau ds, d tau dt, and you can see that's the Jacobian that exactly cancels the Jacobian I would get from converting from st to tau sigma. That's, of course, the whole point of using forms. You don't have to keep calculating those Jacobians. It's all worked out for you. But this is the same Jacobian. Right? In other words, d sigma d tau is equal to this determinant times ds dt. And so that's good. It doesn't depend on my parameterization of my original sphere. Who asked the question? Who asked the question? Raise your hand. It was you. You asked the question. Are you sure that it's uniquely defined? Didn't you ask me that? Who asked me that? You did. It's on recording. We can play it back. You said existence and uniqueness. Yeah, I proved existence by writing it down, and now I've shown you it's unique. It certainly doesn't depend. It's certainly reparameterization invariant. That's cool. But what else can you tell me about the signed area? Now that I know that I don't have to worry about the coordinates on the sample sphere, what else can you tell me? Can it be 2 pi? Can that signed area be 2 pi? How about pi over 7? How about not in units of pi? Can it be things in other units? Could it be 2e? Or twice the speed of light? I guess that has units. I have to non-dimensionalize the speed of light. I'll set it to 1. Could it be 2? Come on. What can it be, the signed area? This is topology. You have a map from the sphere to the sphere. Okay, so it's a map. I forgot to write that down. Maybe that'll make it easier. Okay. So I have a map from S2 to S2. By the way, there's a name for it. It's called pi 2 of S2. This 2 is that 2, and that S2 is that 2. Maps from the sphere to S2. What can you tell me about a map from a sphere to a sphere? The whole sphere to the whole sphere. Imagine the first sphere is a bag. A closed bag, though. A sealed bag. All right? No holes. So I have the sealed bag. One thing I could do is I could take the sealed bag and just like put it on my head. Imagine my head as a sphere. Okay? But you see that I could then shrink the bag to a point and everything would be okay. Agreed? That would be no times around there. That would be no signed area. I could take the bag and I could put this sphere inside it. Then the sphere, the bag, which is that sphere, goes to this sphere once. It covers that sphere once. Or I could take the bag and I could double bag it. And I could have it cover it twice or 3 times. Does that seem clear to you? It took me like 30 years to understand that. So, you know, it's hard. Let me draw it another way for you. I predicted this. Maps from the sphere to the sphere have to cover, when I go around this sphere one time, I have to cover that sphere an integer number of times. How could I cover it half an integer number of times? What happens to, there's no boundary here. Right? This thing doesn't have an edge or a boundary. Every point on that sphere has to go to some point here. It can't go to a whole ring. It can't be that the south pole on this sphere in the sample actually maps out to some curve. some opening. It's not like the rest of the sphere covers the top and then the South Pole gets stretched out around this whole edge. The South Pole has to have one single value here. So it has to close. Let me draw it for you this other way. Topologists find this useful. I understand. They say, here's the sphere. Here's a model for the sphere. You ready? It's a big square. See how that's a sphere? They say it's a sphere because I'm going to say that every point on the boundary is the same. It's all the South Pole, right? This is the South Pole. It would be a terrible projection. Although there are projections of the world that look like that, but instead of being squares, they're circles. Have you seen those where you stretch them out? Yes? They're good. They're good. They're actually not so bad because if you use the North Pole as the place you stretch out, there's no land there anyhow. Right? So you get a really good map of Antarctica, and it gets worse and worse as you go to the boring countries way up north. All right? Greenland, Iceland. There's some little island just north of Norway. What's that? North of Siberia, there's some islands.
Svalbard?
Sorry?
Svalbard.
Are you saying that in English?
That's Norwegian.
No, I'm thinking of the ones past Siberia.
Spitsbergen?
What?
Spitsbergen?
Spitsbergen? Where did they build the doomsday device in Dr. Strangelove? Do you know the answer to that? Okay. So here's the sphere. All right? Now, this is the sphere. That's that sphere. Now, I'm going to put this sphere on that sphere. All right, so this sphere is a yellow square where all the edges are the same. And I have to somehow attach this to this guy. So one thing I could do is I could take this whole thing and crumple it up and just attach it at a little point there. Agreed? All right, so all the points here map to the same point here. The other thing I could do is I could stretch it out like a drum head and have it match the whole thing exactly once. That would be mapping the sphere to the sphere. I could do it instead of doing what I just did. Are you ready? You thought I picked this up and put it here. I could have picked it up and turned it over and put it here. Then I would map out the sphere in the wrong direction. Right? And I'd get minus the sphere, its signed area. The other thing I could do is I could take this thing and up to here, and then I can take the whole thing, right? I'm imagining I have this piece here, and I haven't finished yet, right? It's a piece of paper. I'm laying the piece of paper down, right? And I have yet to lay down the last piece of the paper, right? You ready? Like this. Right, here's the first piece. Right, I'm laying it down neatly like this. It's like putting a protector on your screen. Right, I'm laying it down neatly. And then I get to this point. Instead of laying it down and finishing, what I'm going to do is I'm going to take this and give it a twist and then lay it down. So now what I've done is I've actually taken this thing and I've stretched it out and I've glued it to this thing twice. I can glue it to the frame twice, or I can glue it to the frame 3 times. Does that help? No? Yes? Good. So this area must be 4 pi, that's the area of the sphere, times the integer. It's another topological invariant. Now I'm going to show you another way you can see it, and this one's the best way. Since that's a determinant, it's a Jacobian, what I'm going to do is I'm going to go back to my pre-image. Remember the pre-image? We talked about that? Let me pick all the directions where here, so I'm going to go here. Let me point on the sphere here, all the directions where the director points straight up and down. Points north. Okay? You with me? This is like the pre-image. So here's a place the director points north. So what I'm going to do is I'm going to take whatever the texture is. So you imagine this texture here. Then the director's pointing in all sorts of funny directions on the surface. What I'm going to do is I'm going to just smooth it out. I'm going to say, okay, suppose here it points in a particular direction. There, I need more symbols. Here, let me call this y. This is point y. And suppose point y is here. All I'm going to do on this map here, on this sphere, I'm going to just push it. I'm going to grow y. Everything, this point mapped to y. Now I'm going to say, no, this whole region maps to y. Am I allowed to do that? Sure. Whatever it was doing, I'm just going to push it out. Does that make sense? And then I'm going to push it out even further. So whatever this region of y is, I'm going to try to have y engulf the entire sphere. I can certainly do that. It's a nice smooth deformation. Until I get to a situation where x is almost all by itself, and it's in a whole ocean of y. It's all y. You can imagine doing this with, your favorite continent. All right? You take Australia. Okay? All right? You take Australia. What I'm going to do is imagine that there was land everywhere, Pangea, right? Land everywhere. And I'm just going to shrink the land, making the ocean bigger and bigger and bigger. Right? And as I do it, I'm not going to tear the land. I'm not going to do anything gross to the land. I'm just going to shrink it. I'm going to make all its features smaller and smaller and smaller. But of course, that means that the rate which I change distances is faster and faster. Right? Does that make sense? It used to go from Norway to Finland, and it took this much. Now I go from Norway to Finland a much shorter distance. So as I do that, I'm now concentrating the entire measure here to the point around x. Because dsn and dsn and dtn are 0. Right? Wherever I have this ocean of y, everything's constant. So I've concentrated everything just to the region around x. How convenient. I now have a determinant. Right? So this is just counting. I get some determinant. It counts this determinant times the number of the times 1, because I've hit n. I've hit this direction x once. If I hit the direction x 4 times, I get 4 times this little determinant. Ask me. Do you have a question? Ask me. It's okay. You don't have to be worried. It's a school. No, okay. Do you have a question? Did he predict and say, I bet you're thinking this? No. Okay. So by writing this as a determinant, what I can do is I can show you that this is precisely the same thing as counting the number of times it points in the x direction with sign. So sometimes it points in the x direction and everything's nicely oriented, and sometimes it points in the x direction and everything's oriented backwards. Does that make sense? Do you agree that independent of which direction x is, that integer has to always be the same? How can an integer vary smoothly? Everything I did was smooth. Right? I took whatever the texture was on this and I squished it around, but I didn't tear anything. I get an integer. How is it possible for an integer to change smoothly? Come on, answer the question. I can't see what your shirt says. I think it says Indian food, but I know it doesn't say that. Indian mood. Okay, I couldn't see that. All right. Okay. Yeah. So,
it should be constant.
Constant. So it doesn't matter which way I pick. Every direction I pick must be the same. So what this does is it tells me this is called the degree of the map. It's telling me how many times this thing hits each point here. And the degree doesn't depend on which x I pick, and it's just an integer. Or in this case, 4 pi times an integer because of this funny measure. So all this is telling me is that if I have an ocean, this is telling me that this number, a tilde, is 4 pi times the degree of the map. So it's topological invariant. And the maps, which I told you were called pi 2 of S2, are characterized by this degree. Everyone happy with that? I know it's really hot. right? But I'm up here. I'm at a higher altitude. So let's see. So hot air rises, but the pressure's lower, right? I'm at a higher altitude. So do I win or lose? Yes, you can figure it out.
I'll start calculating.
Yeah, but I'm moving. You guys are sitting still. You're sitting very still. It's frightening. Okay. So, what did I want to tell you? So I want to tell you something which bothered me when I was learning this, which is, why is this called homotopy? Oh, I haven't even used that word yet. Okay, homotopy. So I have this thing. I showed you pi 1 of S1. That was maps from S1 to S1. They were characterized by integers. There was pi 2, of S2. Those were maps from S2 to S2. Also integers. Okay? Somebody asked me, what about the n and minus n, the rotations by pi? Well, you could say those are integers, right? I could write, if I had n goes to minus n, then it's pi 1 of rp1. That's the name of the space. And that's also z. If you want to be fancy, it's half z. That's the same as z. Also characterized by integers. Like so. What are these homotopies? What does homotopy mean? This is the space of maps up to all possible smooth deformations. Two maps that are smoothly deformable from one to the other are called homotopic. I can, because it's like a math institute. How many of you people are mathematician types? How many people are going to get degrees that have the word math in the title? Applied maths. Maths. You could also have maths in the title. Okay? M-A-T-H, asterisk. Okay. And those are physics, engineering. Many of you don't seem to have any majors. Are you students? I don't understand. What? Math? What? Engineering. What kind of engineering? Civil engineering. Okay.
Yeah, physics.
Physics. Okay. Well, so just to be clear on what the maps are, right? Two functions, which is another word for map. Functions are homotopic. I'm sure I'm committing all sorts of mathematical, what's that word? Profanity by saying it this way. Two functions are homotopic, right? Two functions, f and g are homotopic if there exists some function f of x and t, there exists a continuous function, continuous f of x and t, such that f of x and 0 is f of x, and f of x and t is g of x. Look, it's dynamics. Under dynamics, t could be time. It's a stupid parameter here, but it could be time. The point is, under time, functions remain homotopic. Solutions remain homotopic as long as everything's continuous. Oh, do I mean one? One. That's the end point. Thank you. Right? So you see how nice it is? Right? Dynamics, if I had a certain kind of dynamics, this is the initial condition, this is the final condition. As long as everything stays smooth and I don't have any catastrophes or singularities, the dynamics actually is the same as homotopy. So you can always think of it as dynamics instead of anything mathematical like that. So that's what homotopy is about. But then people always tell me about something else. And I never understood what it was. They have this thing called homology. And they have this thing associated with called cohomology. And really, it's much more difficult. It's very, apparently, mathematicians like it because it's easy to calculate these things, but physicists don't like it because it's hard to understand what it is, right? But homology is different, right? Homology and cohomology, remember when we had m was 1 on 2 pi times this integral around gamma of ds theta. So you see, homology is about the paths, and cohomology about this. So remember, I made a point of saying something to you. I said, and I said it on purpose, M doesn't just depend on this, the thing you're integrating, it also depends on the path you took. Right? So homology is telling you about paths you can take, and cohomology is telling you about the things you can integrate. And they're dual, the same way that row vectors and column vectors are dual. When you put them together, you get a number. You know, you take a row vector and you hit it with a column vector, you get a number. See? You give me a path, a cycle, and you give me a function to integrate, and I get a number. Okay, isn't that cool? This is a one cycle. I don't have to have it be ds. I can have it be like this. You're going to go around gamma ds of some function f. This is a one cycle. This is a one form. The whole thing. All right? F ds is called a one form. So you integrate. I can call it omega. Right? The integral. And then you drop the whole thing here. You just write integral omega. See? This is the cycle. The cycle. The one cycle. The one form. They're dual. You give me a one cycle and a one form, and I can make a number out of it. Okay? So I understood that. All right? And then, seems like they're the same thing. Well, they're not, because these are I'm going to show you, these are much more complicated. They can be more complicated. I'll show you that on Friday. But the other thing is they generalize differently. When I wrote things as a determinant, I did that on purpose. I wrote it as a determinant because I want to remind you of your favorite form. What's your favorite form? Come on, you're physicists.
Zero forms?
Zero forms, those are nice, but what's your other favorite form? Every physicist's favorite form. The first time you learn about forms. In physics, somebody always insists on telling you, oh, this is much more conveniently written in terms of forms. Maxwell's equations and fluxes. Fluxes are natural things that you have as forms. So I'll remind you, here I wrote it all down. Okay. Right. You know, you do integrals like this. You do integral E dot ds, right, around over some surface, such that the boundary of the surface is some curve gamma, right? You call this the flux, the electric flux, for instance. You know, Maxwell's equations tell you about time derivatives of the electric flux and how time derivatives of the electric flux give you magnetic fields, right? And time derivatives of magnetic flux give you electric fields. They give you currents and stuff like that. So this is the electric flux. And you know that if you write this in terms of four vectors and all that, it's very elegant, right? The E field, and the B field are components. See, Daryl already said it, of F mu nu, right? This antisymmetric tensor, right? The Maxwell, is it called the Maxwell field strength tensor? Okay, the Maxwell field strength tensor, okay? And you integrate various fluxes of them. And you remember that if you think of F as antisymmetric, if you think of F as a two form, they always have to tell you this. If F is a two form, then Maxwell's equations, oh, I'm going to get it wrong. So I'm going to say Maxwell's equations in vacuum. That way I won't get it wrong. Maxwell in vacuum is dF equals 0 and d star F equals 0. And I can't remember which is which. One of them is always true. One of them is sometimes true. This is one that's always true. Are you staring at me? Is this the one that's always true? Daryl? Yes. Yes, because F is dA, right? And then dF, right? This is always true. Always. Right? And this is J, the current. All right? You can look it up, right? This is just notation, all right? But these are the things that you integrate. These are the fluxes. You're integrating two forms against two cycles. Two cycles are surfaces. And you have the space of all the things that you can integrate, right? And all the things all the things you can integrate and all the surfaces under which you can integrate them. And the thing about homology theory, homology is about fluxes, not determinants. So I said at the beginning, or I said at some point, imagine a situation where you have a director field that's pointing out in every direction. I said you can think of it like lines of electric field. Well, that's just wrong. Okay? Notice that there'd be a difference. I could integrate n.ds over a closed surface. N is the vector. I could have integrated. You could have said, why do you do this complicated integral that was a determinant? Why don't you just integrate n.ds over the whole surface? If it were like an electric field, that would give me the charge inside. Why don't I just do it like charges inside a conductor? And the answer is, because that gives me a different piece of information. N's a unit vector, right? With n being a unit vector, the only thing I can do is calculate that determinant. So, roughly speaking, maybe this is for physicists more than anybody else, homotopy is about this degree, these degrees of maps. And homology is about fluxes and these chains of how you can calculate two forms and calculate fluxes and how fluxes are related to integrals around boundaries and so forth. So to me that was a revelation, because when I talk about just the 1D system, they're the same. When you go to 2 dimensions, you can generalize in 2 different ways. Somebody's dying out there. It's 4:25. I'm lecturing again on Friday, which is perfect because the last bit of the thing now is about crystals. So we're all set up. I've defined for you homotopy. I hope you understand. The most important thing is understanding why this is true. Why it is that maps from the sphere to the sphere have to be characterized by an integer. Do you see that it has to be characterized by an integer? I'm picking on you because you spoke before, right? All right, I'll pick on someone who hasn't spoken, all right, so that I won't finish. You, do you see why that? Yeah, okay, that was a good answer. Okay. So, right, the point is the degree of the map has to be an integer. Right? The number of times it has to point in each direction has to be an integer. And that integral that I showed you measures the degree. Okay, I can do it in a dumb way. It measures the degree if I take this really dumb example that the director just points radially out. Then every point there hits every point on the target sphere once. The degree is 1, and the area I map out is 4 pi. And from that, I can now show you by all these squishes and deformations that I exactly am always calculating the degree from that. Next time, which will be Friday, I'll start talking about how to use this to study defects. Although we already have, we've talked about point defects and line defects. And I'm also then going to try to make this important connection between, and somebody said the word already today, between the defects and the topological defects and Goldstone modes. Very important. Topological defects and Goldstone modes are intimately connected. And again, that's interesting because the soft modes, the hydrodynamical modes, are the Goldstone modes. They're the ones you have to take into account when you're studying long-lived dynamics. And that's exactly where the topological defects live. Okay. All right. Cool off. Still need the microphone. No questions. You're all too hot. It's okay. Nothing. Okay. I'm not speaking to you.
No, not you, I mean, but you come to listen, huh?
Oh, yeah.